the glory of the final answer here. All right. When you see something like this, all of this information, where do you start with it? I'm asking you. So tell me when you see this, what goes on in your mind beside freaking out? Okay. Because I know some people are like, I don't even know where to start. So somebody, Patrick? Okay, so you want to write out all the factors. So that's good. You want to express your function. Ooh, where'd it go? You want to express your function in factored form. And when you say write out all the factors, how many factors did you figure out you're going to write out here? How did you figure that out?
4.
Right, every time we have a non-real 0, we have a partner that goes along with it, even if we don't say it. So if we have I, we also have negative I that comes along with it. And how else do we know that we have 4 factors? What's the other big clue staring you right in the face? Quartic. Quart means 4 quarts to a gallon. Our degree is 4. If your degree is 4, you're going to have 4 linear factors, and you're going to have 4 zeros. Doesn't mean, another word for zeros, folks, that you might see in the books is roots, the roots of the function. Now, sometimes they may be duplicates of each other. That's all right. So you start off, you do 1, 2, 3, 4 sets of parentheses, as Patrick said, and you put your A out front. That's your leading coefficient. If you wanted to get really fancy, you could say A sub 4, because you know when you write this out in polynomial form, your function's going to look something like this. You just keep, we may have all of these terms, we may only have some of them. But that's it in polynomial form. This is standard polynomial form where it's a bunch of addition and subtraction. And this is the same polynomial in completely factored form. So that's a great place to start, knowing what to do with the word quartic. And then Patrick said, I'm looking at my zeros, and even though it only gives me 3, I know I can identify 4. Someone else want to tell me where I go from here? How about someone from table 2? Start filling in your zeros. So every single factor has this form at the beginning: x take away, x take away, x take away, x take away. And then I fill in my zeros. My first zero is -2. My next zero is 2. My next zero is I. And my last zero is -I. And then, of course, I'm going to simplify that because we don't like to have these redundant signs after each other. So this is going to be x plus 2, x minus 2, x minus I, and x plus I. And what's really beautiful about this factored form here is that these 2 pairs of factors that I've underlined, let's do it in different colors. The red pair, they're conjugates of each other. So when you multiply them, you lose your middle term, and you get the difference between perfect squares. These 2, when you multiply them, are conjugates. So when you get them, you get the sum of perfect squares. So here you get x squared minus 4, here you get x squared plus 1. But we don't really need to multiply them yet, because we still have to find the value of a, or a sub 4. We know it's going to go with my lead term of the power of 4. So how do I find, I have 3 unknowns right now. I don't know what x is, I don't know what my y value is, or f of x, and I don't know what a is. So I can't solve one equation if I have 3 pieces that aren't known. So what do? I leave it like that? Andy, you're saying no. Okay. Why?
This is where I was getting stuck. But at this point, is it possible to solve y? Like filling in the function of 3 is the x, putting the other side.
Okay. We're saying that the value of my function when x is 3 is equal to a negative 150. So if you do f of 3 here, everywhere you see an x on the right-hand side, you put a 3, right? And now what can you replace f of 3 with? What does f of 3 equal? Negative 150. So the only way you can finish you can do the value of the first two factors, 5 and 1. But to get the value here, you do have to multiply that out. And again, when we did this back when we were doing the values, the operations with complex numbers, I was really excited saying every time you see this, you're going to get the sum of two perfect squares. You're going to square 3 and get 9, because 3 times 3 is 9. You lose your middle term, and then you get minus I square. Well, I square is negative 1, so this becomes 9 minus a negative 1, which is 9 plus 1, which is 10. So we get a 10 on that side. So now we can solve for A because we get 50A equals negative 150. When we divide both sides by 50, we get A's negative 3. So in completely factored form, I asked you for both forms. You just substitute a 3 right here, a negative 3 right here for A. And guess what? We know whatever the leading coefficient is in the factored form is exactly the same number here. So you know your first term here, negative 3x to the 4th. That's all you can tell right now. So to get the rest of this, you multiply all this out. You have x squared minus 4 times x squared plus 1. You multiply that out and then multiply every single thing by negative 3, and you'll get your polynomial. The answers are on the back, so you can check it. Okay, that's just an exercise in multiplication using FOIL. Okay. Okay, so yep, Christopher?
In 3 minus I plus I.
Yeah. Yeah.
When you're like, don't you have to do the whole constant block there?
Well, because these are conjugates, which means that you have exactly the same numbers in each slot except one subtraction and one's addition, your middle term and your outer term are opposites of each other. Negative 3i and positive 3i, they go to 0. So that's why I don't even have to bother with the middle term there. So I just get 3 times 3, which is 9, and negative I times I is negative I squared. Okay? And the same thing happens here, Christopher, with x plus 2x minus 2. They're conjugates. So you don't have to worry about the middle term. You just square the x, you square the 2, and because the signs are opposite here, it's minus 4. But with complex or imaginary numbers, it becomes the sum of two perfect squares. 9's a perfect square and 1's a perfect square. Yep.
There's a couple less.
Yep.
With that, except it was like 8 minus x minus I.
All right, so in other words, if you were told that your zeros look like this, I'm just going to pick something, x plus I, and your other 0 is x minus I. Okay. Well, I can't answer it if you don't have the problem.
No, it was like, oh, sorry, it was x minus I. It's x.
Right. The point here is it doesn't matter how many zeros you have. If I tell you one of your zeros is 8 plus I, the other one that comes along for free is the conjugate. So just put it in parentheses and treat it as a number. Like think of that as 8 and think of that as 10 if you want. It doesn't matter. When you write out your parentheses, your factors, you say 8, take away this number, keep it in there, don't let it scare you, and then 8, take away this number. And now when you drop your parentheses, you just have to remember to distribute the minus sign. So it looks like this. It's actually exactly like it looks in each of these, but they trade places. It's x take away 8, take away I, because you distribute the negative sign through here. And then when you distribute the sign through here, you get x take away minus I, and x take away 8 plus I. Now, if I asked you to multiply these two things, you could go crazy. But there's a very cute little strategy. Look. Put parentheses around there. This is that whole visual thing. Just think of this as one big letter like A. And this is what it looks like, folks. Big capital A minus I. Get out of there. Get out. Ooh. So just if I gave you this problem and asked you to multiply this problem, what name do I apply to these two factors? They're conjugates of each other. And it's very simple once you see, put the parentheses here, because what do? You square the first term. So you square the x minus 8. You know it's going to be the sum of two things squared. And when you get negative I square, you get a plus 1 there. So you're all done because you know how to square x minus 8. It's x squared minus 16x plus 64, and then the plus 1 makes it a 65. So that's how you would multiply that out. So the trick here is to just put the parentheses around these two. Does that help you, Caitlin? Okay. All right, so I did want to show you, because one of my students in my first class asked me about this second problem on the homework. And someone was working on this in the math studio, and they hadn't completely read it. It says, I sent everybody an email and told you to totally disregard this. I sent everyone an email and I said, just do the methods we used in class by using a graphing utility. And a lot of people didn't read this. Find the zeros by using a graphing utility. So you either use GeoGebra, put this into GeoGebra, and if you do that into GeoGebra, oops, or your calculator, you're going to see this graph go straight through -1. So you say, okay, I know a 0, it's -1. So then you have to use long division, and you have to do x take away -1 becomes x plus 1, and you have to put it in, you have to divide these two out. You could use long division or synthetic, whatever you want. And then what you're going to have left up here is going to be some type of cubic. And then you have to use a graphing utility. You put that cubic in and you find another 0. And then I think it's another -1. And then you divide that and you're going to get some kind of quadratic up there. And then you use your quadratic formula. So you just keep repeating that process. If you have a 4th degree, you're going to have to use your graphing calculator or your GeoGebra twice till you get to a quadratic to solve it. If you had a 5th degree there, you'd have to use your graphing utility 3 times before you could get to a quadratic. Because once we get a quadratic, we're okay. We can use the quadratic formula to finish it off. So you have 2 or 3 of these x to the 4th polynomials in this homework assignment. So I'm not surprised that some of you, if you waited till last night, you didn't get through it. So take some time over the weekend and try to finish that up, because you'll see this again. Okay, today we're going to start rational functions, and we're a little late here. I was hoping we wouldn't take 25 minutes, so I might just speed up a little teeny bit. Rational function, when you see the word rational, I hope you think of me. No, I hope you think of the word ratio. Ratio means the comparison of two quantities through division. So in this particular case, we're actually comparing two functions through division, and both the numerator and denominator are polynomial functions. So if you covered up this denominator, if I took my arm and covered up the denominator, the top looks like a quadratic function. And if I covered up the numerator and we just had that written out, it would be some type of cubic. So I did you a favor here by factoring the denominator, because now we have to worry a little bit, because with polynomial functions, remember, polynomial functions all on their own, the domain's all real numbers. But now that we have a polynomial function in the denominator, we have to be concerned again about the denominator not being set equal to 0, not equaling 0, because we can't divide by 0. It's undefined. So by factoring this, I did you a favor because it's really easy to look at these factors to see what the domain is. So the domain here, and this is the one time when using set builder notation is real quick and easy. The domain, remember, is a set of all real numbers x, and then sometimes we have some excluded values that can't get in the front door. The bouncer kicks them out. So what's going to be the excluded values for this domain? Drew, can you give me one of them? 4, because if I put a 4 in there, 4 take away 4 is 0, and that makes the whole thing 0. Absolutely. So 4 can't get into the door. 4 is excluded. X can't be a 4. Okay. Liza, can you give me another one? 0, right? Because if this first factor is 0, doesn't matter that the next factor is -4 and the next factor is 2, because 0 times anything is 0. So that's definitely not allowed in the club. And one last one. Chris? We took care of this one. We took care of that one. So -2. So there's my domain. So you can see this time, set builder notation, we haven't been using it very much, but it makes it real quick and easy, very efficient to represent the domain. As you know, with MyMathLab, you're going to have to write this in interval notation. So it's kind of helpful to actually just do your little real number line like this, which in a minute will become your x-axis when we start graphing these things. And you know that you have open circles at each one of these. And your domain are all numbers that's to the left of -2, in between -2 and 0, not counting 0, or -2, same thing with 0 to 4, and 4 out to infinity. So you have 3 separate intervals here, 4 separate intervals. So if you were showing this on MyMathLab with interval notation, you'd have to say, my domain is all the numbers from -infinity to -2, and I union that set of numbers with all the numbers from -2 to 0, and then I union that set of numbers with all the numbers from 0 to 4, and then finally I union that set of numbers with all numbers from 4 to positive infinity. So it's kind of a pain to write that all out in interval notation, but that's what you have to do. So if you have 3 zeros, it's going to chunk your real number line up into 4 separate intervals. If you had 2 zeros, you'd have 3 intervals. If you had 1 zero, of course, it cuts it into 2 intervals. So that's how you find the domain of a polynomial function. And that's what number 2 is. I just did it all under number 1. And so now we're going to start investigating graphing rational functions. They're going to look slightly different than any function you've done to this point. Some of the ideas that you used are going to come in handy. All your work with transformations is going to help you with all of your activities today. Because all we're going to do is we're going to either do a transformation on this first function or a transformation on our second function right here, 1 over x squared. That's all we're going to do. We're just going to do shifts, vertical, horizontal shifts of these functions. So once we figure out what these basic functions look like, or parent functions, then it's simple to use all of our knowledge from transformation of functions to graph after this. So here's our very first, the simplest possible rational function we can have. F of x equals 1 over x. Okay, so that's called the parent function. It's a basic function, but it has another name because of what it does to every x. No matter what x I put in here, what's going to come out of my function machine? How could you describe the relationship between the input and the output? There's a word for it. Caitlin? The reciprocals, right? They're reciprocals of each other. If x is the number 10 and I put it in here, it comes out being 1/10. If x is the number -5, it comes out being -1 over 5. If I put in the number 1/1000th and I put it in here, it flips it, it becomes 1,000. So this is called the reciprocal function. So whatever you put in for x, you just simply think of it as a fraction in your mind or a whole number with a denominator of 1, and then you just invert it. That's all it does. So let's suppose I realize now that I have this polynomial in the denominator. Look, my polynomial in the numerator is a constant function, 1. It's not very exciting. It just goes along being 1 all the time. The polynomial in my denominator is linear. It's just x. It's a linear polynomial. G of x equals x. Not too exciting either, but pretty simple. We want to stay simple right now. And if I actually put a little exponent on that x, it would have a 1 there. Okay. So if I asked you what the domain is here of f, what would you say, Tom? What would be the domain of f here? You can use set builder notation or interval or words, whatever you want. Yep. So the excluded value of 0. So the domain is the set of all x such that x can't be 0. Remember, your domain is a set of numbers. It's not 1 or 2 or 3 or 4 excluded values. Interval notation. We have 2 intervals since we only have 1 excluded value. All right. So what's really interesting here is when you go to graph this function, you can't have any part of your graph cross the y-axis. Why not? Why can't my graph cross the, why can't I have a y-intercept? Never mind, okay. Thank you for trying. Caitlin? I mean, Katie? Catherine? Catherine, Caitlin, both Katies, okay. Katie? Right, any y-intercept. Think of any y-intercept. If you're sitting on this y-axis, what's your x value? 0. Can x be 0 here? What did Tom just tell us? It's excluded. You have no y-intercept here. So we can't have this solid line here going through this axis because our graph's never going to cross it. So what we do is we write a vertical dotted line to say, hey, I'm not part of the graph, but I'm just kind of putting this in as a little help for you in sketching this graph. What's the equation of that dotted line? It's a vertical line. What's the equation look like? So it's a linear function. What's it look like? X equals 0. Right there. Oh, I told you. Oh, shoot. I gave all the fun away. We call that line a vertical asymptote. You could never, ever, ever, your graph will never, ever cross your vertical asymptote, because if it did, then you're making up a whole new mathematics, and you know what the value is when you divide by 0. So vertical asymptote never gets crossed, okay, ever. So you might know some people like that in your life that you never want to cross, right? That's your vertical asymptote. All right. So what we really want to do here is we want to see what the behavior, what's the behavior of my function as I get really close to that number 0. And if you look at this, your graph is going to approach 0 from 2 directions, from the right-hand side of your number line, your x-axis here, and from the left-hand side. So let's just play around with this. Let's pick some values and see what happens to the value of my function when I get really close to this excluded value. There must be a reason why this value is excluded. We know what the reason is. But what happens if you hang out with this number, you try to hang out with it? What happens to your behavior? All right, so we're going to see. So we're going to take the number 1. If I put 1 in for x, what's the value of my function? What's f of 1? It's 1, because 1 over 1 is 1. Okay, so I'm going to go down here and I'm going to graph that. So at 1, I'm 1. So far, that doesn't seem like anything out of the ordinary. Okay, so instead of looking at decimals here, since I'm inverting everything, it might be really helpful to me to just write these in fraction form like this, since all I'm going to do is invert them. That's what my reciprocal function does. So when I put a half into my function, what's going to be the value of my function when x equals a half? Yes, it would be 2, Dylan. Yep. So when I go halfway between 1 and 0, I'm up to 2. Okay, so looks like I'm getting a little taller. All right. All right, now I'm going to go into 1/10. It's going to be really hard for me to write because this pen isn't a very fine pen here. It's going to be kind of hard to get that close. But what's the value of my function when my x value is 1/10? What do you think it is, Dylan? 10. All right, so I'm going to take a look at that and see how I do. I'm going to be really, really close. I better use a different color here because I have that vertical asymptote there. I'm really close to. There we go. All right. Now, what happens when I get even closer? I go 1/100th of the way to the right of 0 from 0. What will be my value for my function? 100. And what if I'm only 1,000th to the right of 0? What's the value of my function? 1,000. And what if I'm 1/1,000,000th to the right of 0? What's the value of my function? 1,000,000. What if I'm 1/1000,000th to the right of my 0? What's the value of my function? What's the reciprocal of 1/1,000,000,000? Billion. All right. Do you get what's happening, folks? The closer and closer you get to this 0, the value of your function is shooting right out through the roof, going into the heavens. It's increasing very rapidly without bound. Nothing's going to stop it. It blows up. It becomes really crazy, right? So you don't want to hang out with 0. So you're going to hug. You're going to get as close as you possibly can imagine to that y-axis, to that dotted green line, but you'll never, ever cross it.
And it never becomes a straight line either. It always has a...
It's always curving just a little, but it's getting, it's like almost infinitesimal, the distance there, right? All right. So how do we talk about that behavior with math language and symbols? So notice we're approaching one number here. We're approaching that excluded number. Okay, so these are the numbers that your parents tell you don't hang out with these numbers. Okay, because you're going to get really crazy here. Yeah, William. There are situations, yes. There are applications, and they're in the 3.5, this section. There's applications, and you'll see them. Most of the applications, a lot of times, will have to do with something that we're going to call the horizontal asymptote, where if you think about the carrying capacity of the Earth and the environment, there's going to be some number of people that the Earth can sustain. And as our population can approach that, but it's never really, I mean, we haven't hit it yet, but there is, and depending on what book you read, there's no science about this right now because everybody has a different model for it. So you can think about a carrying capacity of the Earth as the people continue to grow. So you're looking at your end behavior. The value of that, the population, right, is approaching this particular like level that we hope we never get to, because we're going to run out of all our resources. That's one idea. There's lots of functions, particularly growth functions. This idea, right off the top of my head, I'm not like thinking about it, but if I thought about it a little bit more, I could probably come up with one. If we went and looked in my math lab, I think we'd find one pretty quickly. It usually has to do, well, we'll just leave it there and I'll think about it a little more. All right, so here, folks. Everything we just showed in this table is reflected in this sentence, and then we're going to do a shorthand notation for it. It says here, as the x values approach 0, that's our excluded value. We're approaching 0 from the right-hand side. That's the new language. Really, that's the big new language for you today, is from the right and from the left. This idea from the right and from the left. Because you're kind of coming in close to this number from both directions. The value of your function is approaching what as you come in and get closer and closer? What's happening to the value of your function? What is it approaching? Infinity. Oops. Infinity. So the way we write that is right here. This notation. As x approaches this excluded value 0 from the right-hand side, that's the little plus symbol here. That takes the place of this language here from the right. That's the plus, comma. The value of my function, my y values, shoot up to infinity. Boom. So that whole sentence can be done with this little bit of shorthand notation. So now the question is, what happens, and why are all these y values positive? Why are all the values of my function that I've put in this table positive? Why is my end result positive? I'm doing a division problem, right? What's the sign of my numerator? Positive. If I'm coming in to 0 from the right, what's going to be the sign of all my x values? Positive. And when I divide a positive by a positive, I get positive. All right, let's take a look at the other way. What do you think is going to happen when I come in from the left? Here's my function, f of x equals 1 over x. My numerator is positive, and I'm going to be picking all x values that are, what's the sign of all my x values now? If I'm coming in from the left, I'm picking x's to the left of 0. Negative. So when I divide a positive by a negative, what's the result of my function value going to be? What's the sign? Negative. So now when I graph, I'm not going to be, ooh, I moved this. I can't cross there. How did that? There we go. That's better. So now instead of having my function be above the x-axis, I've got to be below. So let's do the same thing. When I put a negative 1 in, look, here I was 1, 1. What happens now when I put negative 1 into my reciprocal function? What am I going to be? Negative 1, right? F of negative 1 is 1 divided by negative 1, which is negative 1. So at 1, negative 1, I'm negative 1. So at negative 1, I'm negative 1. Already, I hope you can start to see what type of symmetry you're going to have. Because when you put in opposite x values, look what happened to your y values. They're opposite. Okay, when I put in negative 1/2, I'm going to be negative 2, and we keep playing this same game. We hug, 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 all the way to where? Negative infinity. So as x approaches 0 from the left, my value of my function f of x approaches negative infinity. So that's the beginning of this graph, but I haven't finished it. I've just looked at my behavior near this excluded value. So how do I finish the graph? I say, hey, what happens as x gets big, big, big towards negative infinity? And what happens to the value of my function as x goes towards negative infinity? That's called the end behavior. So let's take a look at the end behavior here. So I'm going to do it back on this graph right here. So what happens when x is 5? What's going to be the value of my function at 5? So I'm moving out now, out towards the right. What's the value of my function when x is 5? F of 5 is going to be what? 1/5. So I'm right here, 1/5. So I'm coming down like this. What happens when I'm out at 10? 1/10. Oh man, I don't know if I can get that close. What happens when I'm out at 1,000? 1,000. What happens when I'm out at 1,000,000? 1/1,000,000th. What's the value of this getting closer and closer to? What number is it getting closer and closer to? 0, but it's never going to be 0. So as x goes towards positive infinity, my function gets really, really small. It approaches 0. It gets smaller and smaller and smaller. My denominator is getting huge, but my numerator is still staying at 1. That gives me a really small number. And as x goes towards negative infinity, my function also approaches 0. So I'm now going to do a very similar thing here. All right, I didn't draw it quite as nice. So there's my reciprocal function. It has symmetry about the origin. The distance here is the same as the distance here. It has origin symmetry, or another word for that is odd symmetry. You've just rotated this 180 degrees, this particular graph. Okay, so that's your reciprocal function. We didn't look at x and y intercepts. So let's take a look at that. Does 1 over x have x or y intercepts? We've already taken care of the fact that there's no way it can have a y-intercept because x can't be 0. So f of 0 is undefined. We can't cross our vertical asymptote. So can it have an x-intercept? Well, to have an x-intercept, you say, what's the value of x that makes my function equal to 0, my y value equal to 0? So you say, okay, my function's 1 over x. When does that equal 0? When can 1 over x equal 0? Never, because look, the only way that could equal 0 is to have a 0 in your numerator. That's never going to happen because your numerator is 1. So you have no x-intercept and you have no y-intercept. And if you look at this function, you see you don't cross the x-axis, you get really close to it, and you don't cross the y-axis. We call this vertical line the vertical asymptote. Its equation's x equals 0. We call the line, the value of our function that we approach as x goes to positive and negative infinity, the horizontal asymptote. And while it's impossible to cross your vertical asymptote, there are situations where you can cross your horizontal asymptote. Not in this case. And the equation for the horizontal asymptote is the value of your function y equals 0. So let's take a look at your very first exercise today. Keep this picture in mind. This is the picture you want to keep in mind as a parent function. So if you look at your very first activity right here, what parent function am I transforming here? 1 over x or 1 over x squared? Which one am I transforming? 1 over x. So I'm going to take that picture of the reciprocal function we just looked at, and I'm going to do something to it. I'm either going to be moving it horizontally or moving it vertically. So if I look at this function, what does this function, what are the transformations that's happened to my parent function, 1 over x? How is it moved? Isabel? To the right 5, exactly. So to graph this function, all you do is come back here and you literally take this thing and you move it. Look, this is what's so great about technology. I just moved this to the right 5 like that. Wow. Right? That's all I did. I literally moved it to the right 5. Because now my excluded value that's not getting in the club is 5, not 0 anymore. Okay, so that's kind of fun you're going to have in a few minutes. All right, let's look at one more parent function. The parent function is 1 over x squared. I do want to point out one more thing, please. Just have your attention for 1 minute here. Because you say, you know, I learned all this stuff about polynomial functions and multiplicities. Does that come into play here? And most books never talk about this. But x has the exponent 1, which is an odd multiplicity. And we learned that when you have an odd multiplicity, the function changes sign at that 0 when it crosses the x-axis. Well, at x equals 0, we're not defined. So literally our graph isn't crossing anywhere. But look at what happened to the sign of your function as you approach that 0. You're negative on this side of that 0. And just like an odd multiplicity, once you take one step to the other side of that 0, even though it's not officially a 0, you're positive. So the sign of your function changes when you have an odd multiplicity there, or an odd exponent. So you may now, if you think about it, look at this one. Here you have an even exponent. So here you say, with even exponents, I never change sign. I just kind of touched my x-axis at that spot and my sign stayed the same. So you should be expecting similar behavior. So again, we have exactly the same with x squared. We have exactly the same vertical asymptote. I'm going to go through this quickly so you have time to start your activities. So our vertical asymptote here, remember a vertical line always has x equals some type of constant. In this case, x equals 0 is my vertical asymptote. And that says as x approaches 0, what's happening to the value of my function? Well, let's see. Now when I'm 1, I'm still 1. But now when I'm a half, I get squared. I become a fourth. And then you take the reciprocal of 1/4. So you're jumping up even quicker. There you are. You're getting even, you're going to hug that y-axis even faster. You're still shooting up there. But now when you take the step over the other side, you're not changing your sign, because now when you're -1, 1 over -1 squared is still 1. So just like with your even multiplicity, you do not change the sign near that, even though it's not a 0. It would have been if it was allowed. So that's what the graph looks like. And your end behavior says, what happens to this function as x goes towards positive infinity? Well, you're going to get closer to 0 faster. F of x approaches 0. So you still have your x-axis here as your horizontal asymptote. So all you have to do, these are just quick sketches, folks. So you don't have to like be, perfect here. You just get really close. You hug the x-axis. And this is 1 over x squared. This is your other parent function. Yep. Yes. So I didn't do that up here, did I? Thank you. So as x approaches 0 from the right, the value of your function approaches infinity. As x approaches 0 from the left, the value of your function approaches infinity. So notice you don't change sign. Everything's above your x-axis. So let's take a look at, suppose I gave you this as your new function. G of x equals 1 over x squared, take away 5. What's going to happen to that parent function? Same exact shape, same exact function. What's going to happen to it? Dylan, I know you can tell me this one. What's the transformation? We're outside of our function, so we've already calculated our f value. So this is our y value, and then we're going to subtract 5 from all our y values. So which way does it move when we're subtracting down? So this thing, watch what happens. All I'm going to do is take this and move it down. So look, right now, my horizontal asymptote, the number I approach is 0. I'm just going to move that down to 5 units, and there you go. That's all you do. You just move it down. Have fun. You got some exercises to do. These are fun, 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 till your daddy takes a T-bird away. Okay, okay.